well, thank you. I'm so. I wish I could be there. Actually, it's warmer in Montreal today than it is in where I am in West Lafayette, Indiana. So anyway, so I'm just gonna say hi to everybody in person. Then I'm gonna switch over to just display my screen, and I'll be able to hear you. And I don't know whether I was able to see you. So anyway, okay, so now I'm going to come over here, and there we go. So I'm going to start with this. So we're going real old school. So the title is Gambling with Gambit. Oh, and for some reason it goes on my own here. Oh, hold on. I don't want it to do that. Why is it? Okay.
Maybe you have to share a screen.
I thought I did share screen. Oh, start share. There we go. Okay, start sharing. Am I sharing now? Can you see the? Okay.
Hello, just a moment.
I'm not ready to talk to. Let's see. Well, the full screen. Let's hope it doesn't go ahead again.
Yes.
Oh,
Just a minute. I have
there we go. Okay, good. Now it's not going to do that. Gambling with Gambit. Okay, so I wanted to have a precise definition, so I looked up a definition about what is to gamble, and it's to skip about, as in dancing or playing, to frolic. So think of, a lamb in a field or something, or a colt or something like this. So this is how I feel sometimes working with Gambit. So it's good. So I'm going back to first contact. So what I've done is I found the first email I sent to Mark. So you should note here the date. It's April 20th of April 1993. It's sent to Mark Brandeis. I'm not sure he even got his PhD yet, and it's a typical subject line for someone who wants to be polite about maybe a bug they found, and so it's a bug or feature. So for all you young people in the audience, just be careful what you send an email, because 25 years from now, some old guy could put it on the screen. So that's copied from the header of my first email to him, and so I got my first response from him, and I'll just excerpt one of the paragraphs. And
that was my first mistake.
C'est tellement un bon feature, ça a crashé le stream.
The best. Hey. It's time.
Okay. We're connected again. Okay, good.
Go back.
Are we okay?
Yep. Yes.
Okay, good. So I want to talk about three applications and see three sort of different areas, and I imagine, many people in the room have applications, so I don't want to spend too much time, but I wanted to sort of highlight things that I thought highlighted some of the strengths of Gambit and what made it fun. So the first, one of the really early applications I did was genetic 90. So genetic programming is sort of out of style now, but there was a time people programs image problems, and I was working on image processing, so I wanted to solve image processing problems. So in image processing, you have a lot of data. So each program is run on each pixel. So you got 250,000 pixels per image, and there are hundreds of programs per generation. So you're talking about a lot of computation. So this was early on in Gambit's development. So one of the things I found was that when you're doing genetic programming, the compile time comes into the problem too, because I was actually compiling these programs before I ran them, and so if the compiler took a long time, that's a problem. That's part of your evolutionary time. So what I did was that's when I started getting into Gambit's compiler, and Gambit has a representation of sets of variables and labels and whatever. So I redid that representation because I was doing a primitive version of what the fancy name is Gambit forensics, trying to figure out where the compiler was spending its time. So that tripled the speed of the compiler. So you were just given a lecture on the Gambit virtual machine, and the front end of Gambit does something called lambda lifting, which converts a procedure's free variables to explicit arguments. Now, it still doesn't work too well with the register allocator, so using knowledge of the front end and the Gambit virtual machine, I ended up doing it by hand. So I wrote the code so there were no free variables. Everything was an explicit argument, and the result was good. I think it was the fastest genetic programming system in existence. And there are systems written in assembler, there are systems written in C, and it had an overhead of 11 machine cycles per pixel. So that's pretty good. That's pretty good. So I can't see you, but I can hear you. Are there any questions? No? Okay. So this might be a lot shorter talk than I imagined. I haven't given a talk this way before. Okay, so that's the first application. The second application was quite a bit longer. So I was teaching a course, a graduate course in numerical partial differential equations, and I was quite unhappy. It's a joint computer science mathematics course, so I wanted there to be some application content, and I was quite unhappy with the projects that the students would hand in. If every student started from scratch, they couldn't get anywhere in a semester. So I decided to provide a base library for the basic things that I would cover in class, and then each student would do a project. They would solve some problem that wasn't immediately solvable by the base library. So I developed this over quite a few years. So it's a functional object-oriented system for solving elliptic, parabolic, hyperbolic PDEs. You don't need to know what that means, using the finite element method in two space dimensions. So it was used as a pedagogical tool to teach upper level graduate students, and they had to write code for a project to add to the library. So most of the time, here is another instance where Gambit's strength came in. Most of the time is taken up in something called sparse matrix vector multiplication. So these matrices are very sparse. So they might have, let's say, 15,000 rows and 15,000 columns, but there's only like 7 or 10 or a dozen non-zero elements in a row. So all the elements are zero. So I mean, that's very sparse. And most of the time, and solution time, is taken up in multiplying matrices with that structure by vectors. And that's limited in speed by the time for memory access. So it's limited in speed by how quickly you can read in the coefficients of the matrix. And because it's limited in speed by the time for memory access, it ran as fast in Gambit as in C. I rewrote that special routine in C just to time it, and things went as fast. So that's all I want to say about that thing. This is a very strange experience.
It's okay, we're here.
Okay, good. And the object-oriented system I used for this was Maroon. I'll mention a few things about that in a minute. So the last application I want to talk about is a homework on the web system. Now, have you used homework on the web? Things that correct your homework automatically in math and physics classes. Have you used those things? Maybe not. Okay. Well, here they're used a lot because we have classes with 1,500 students in them or more, and so we don't grade homework by hand anymore. It's all graded by computer. And if you use any of those systems, you'll find out that many times you have to put the answer in a particular form. I mean, if the answer's a half and you write 2/4, it'll say, no, that's wrong. I want a half. And then there are other things where in some ways you could type in an incorrect answer, but it'll get confused and it will accept it. So to my knowledge, and I've looked at a lot of these systems, this was the only system that accepted all correct answers and rejected all incorrect answers. Now, I thought I had to say more than just that sentence because you would say, well, it's obvious that a system would have to do that, but I'm telling you, it doesn't happen. So one of the aspects of it was that computer arithmetic is often not like real arithmetic. I mean, like hand arithmetic. You know, to a student, 0.1 is 1/10. But in a computer program, if you write 0.1, it's usually translated to the floating point number closest to 1/10. So, I mean, that's pretty easy to do in Scheme or in Gambit. I don't know if you know, but if you want 0.1 to be exact, you just append a pound sign, let's see, E pound sign in front of it. And then the reader interprets it as an exact number. So that's pretty easy. But we also needed to have some symbolic manipulations, some symbolic processing to solve some algebra problems. And Mark helped me with integrating Maple. So we just started up 5 Maple processes in the background for back-end symbolic processing. The Maple Corporation sort of yelled at me and told me first that it wasn't possible to do that, and then they told me that I wasn't allowed to do that because we only had individual student and faculty licenses and not so-called server licenses. Well, we told them, okay, we won't tell you about it. So this was actually used in a class, trigonometry. We don't teach that particular class anymore, but it was used by a lot of students. It was used by 1,400 students every year, 600 in the fall, 800 in the spring. The data storage, I didn't want to use. I mean, if you think about it, when you try to describe different kinds of problems and the answers you might get, I mean, a database where each, was fixed size. I don't know. I didn't want to use a database. S expressions is real simple, and so we just wrote using pretty print to write a representation of what this work the students had done so far. And it turns out that the original revision control system was written by a guy here at Purdue. I used to teach for Purdue, but now I'm retired. So it was written by a guy here at Purdue, Walter Tishy, and I'm an old guy, so I still use the original one. So there we go. So we used RCS. And it ran interpreted on an UltraSpark system. It ran interpreted because I wanted to, if there was a problem, I didn't want it to crash the whole system. I didn't want it to corrupt things, and so Interpreted offered a way to offer a bit more safety, a bit more error catching without bulking up binaries, and it satisfied about 40,000 transactions an hour. That's not a lot of transactions, but it's not so bad when you're doing that, every day, day in and day out, and so I was quite happy with that. But like I said, they're not teaching that course anymore. So so that's what I wanted to say about application. So I hope that I highlighted some of the properties of Gambit that allowed some of this to be done. Are there any comments so far, or nothing? Okay. Let me go on now to library. So these are things where I contributed or something a little bit more low level, either to Gambit or to well, the first one is not to Gambit directly, but the first one is the library Maroon. And I need to talk about that because I've used that a lot over the past 20 years. And it's an object system originally written by Christian Canet of Paris. And it was one of the pieces of software that really helped me understand what software design is all about. Because he had a very specific idea in mind, and he chose what I consider to be a very sweet design point, okay? So I want to mention some of these things he chose. So he chose a single inheritance. So what is the alternative? The alternative is multiple inheritance, but Canet, who's a very bright guy, said, I don't really understand multiple inheritance. So I'm going to stick with something I understand. I'm sure he understands it a lot better than me or most people in the room there. But he said, I want to stick with single inheritance. And then instead of Java style functions, or that are sort of contained in a class, at least that's my understanding of them, at least early on. I don't know recent Java or whatever. He chose to have generic functions with methods. And that's more like the common Lisp object system. And I like that style of, as a mathematician, I like that style of thinking because, you apply an operator to a vector. Well, what's a vector? I mean, it could be something in Rn, it could be polynomials, it could be functions, it could be lots of different things, but you're still just applying an operator to a vector. And you define methods to specialize that, each one of these things to the specific representation or of objects you're working with. Another thing he decided to do was to have multiple argument method dispatch. And that's useful for quite complicated things where the method you want to apply depends not only on the argument, on the type of one of the arguments, but on the type maybe of multiple arguments. But he also had single argument dispatch as a very fast special case. So if, in the common case of single, that what method you use depends only on the type or the class of one of the arguments, his thing was very fast. So, so he thought.
Waiting for that to happen. Watching my Wi-Fi sit. Okay, I have Wi-Fi. How long will it go?
I have to set up connection again.
So last time he called back, so. Est-ce que vous devez brancher votre... Il y a aussi la batterie, mais je sais juste 12%. Votre batterie est à 12%. Yeah, you're back. Are you...
Am I breaking up?
No. Well, the connection was lost, and right now we don't know if your voice is coming in clearly.
Okay, I can hear you. Can you hear me?
Yep, sounds good.
Sounds good. If I talk too fast, maybe I overload things.
I think that's how.
Okay, so anyway, you can modify the behavior of Maroon by writing Maroon code. And that type of thing is called a meta-object protocol. And Connect thought, so the common Lisp allows you to modify it at runtime. It allows you to modify the object system at runtime, which is pretty cool when you see it in practice, but it also complicates the design of the system a lot. And so Connect chose a compile time mock. So, ahead of time, you can say, okay, for this particular program, I want to use Maroon modified in a certain way, and but you have to do that at compile time, and then for your whole program, it acts like this. So one thing I did, once I decided I really liked Maroon, I wanted it to run very fast, and then with Mark's help, it's very closely integrated into Gambit. One of the tags that he left out of that big slide of different type tags is a Maroon type tag. So there is a Maroon type tag in Gambit, and object, class access is object access. Referring to a field in an object is the same as a vector rep. So if you want things to be unsafe, I mean, it's just very, very fast. So that was one of my first experiences, trying to integrate something into Gambit, and it also allows me to advertise this in case you're looking, and it has a lot of syntactic. There's a saying that. What is it? Too much syntactic sugar causes cancer of the semicolon. But that's a joke. Okay, so there's a lot of syntactic sugar in Maroon, but I find it very, very helpful. Okay, so I guess I want to get to the big thing now, and the big thing is big nums. Okay, so what are big nums? Big nums are integers of arbitrary size, and in June of 1998, Mark asked me something that I ended up spending about 10 years on. If I'd like to start like a project to rewrite Gambit's big num library based on this paper. So this is something of a famous paper, Reconfigurable, Retargetable Big Nums, a case study in efficient portable Lisp system building. And I don't know if Mark has ever told you, but one of the big design goals of Gambit is portability. Okay, he wants it to run, I'm speaking for him now so he can correct me. He wants it to run on every system. Every system with a C compiler or now with a JavaScript interpreter or whatever. And so he wants it to run on word things with 32-bit words, 64-bit words, big endian, little endian, this glibc or muscle or whatever the other alternate small C libraries are. He wants it to run on everything. So I think a paper with this title is really, playing to Mark's base. So let me tell you what John L. White's big idea is, because it's a great idea. So his idea is to introduce a small number of primitives, okay? And these primitives can be written in whatever your base language is. C, assembly, Java, Python, whatever, okay? So once you write these small number of primitives, you write the rest of the system in scheme. So these, I was going to put a slide up with all the primitives in it. There's about maybe a dozen. That's it. And each one can be written in as a C macro in one line of, well, maybe some of the more complicated ones because are a few lines of 80 character C. But anyway, each one of these dozen things has a very primitive definition. And then the rest of it's written in C. So in this primitive definition, the way that that Mark arranged things, big nums are just long bits of long strings of bits, and you access these long strings of bits in certain chunks, and the size of the chunks are appropriate for the operation. So, like on a 64-bit, on an x86 64, you would use 64 bits for addition and subtraction. You might use 32 bits for multiplication. Even smaller for specialized operations. So on x86 32, where you don't have 64-bit registers, you still might use 64 bits for addition and subtraction with long, and then only 16 bits for multiplication. It's all this stuff is abstracted out. Once you have these 13 primitives and a few constants that tell you the parameters of your system, you're good. And this is sort of a joke, but it's true. The universal backend accesses big nums in 14-bit chunks, which to me seems kind of silly, but I know why it does it. Okay, so this leads to maximum portability. And writing the library in Scheme implies that you can try more sophisticated algorithms. And in fact, one of the algorithms that's currently in the GMP, the GNU multi-precision library, was first tried in Gambit. And I told one of the authors of GMP about it, and he adapted it and improved it and wrote 2 papers about it. And it's now in GMP. So, being able to try more sophisticated algorithms sometimes lead to good places. Okay, so, and also there was only 1 or 2 people writing this library. Okay, so I was the main person writing it with advice from Mark. So we couldn't spend a whole lot of time writing low-level code in assembly or C or having multiple versions of algorithms for numbers of different, for different sizes. So we had to, using a very high level of abstraction, choosing very few but sophisticated algorithms helped a lot. So that was John L. White's big idea. And I think in Gambit, it's been implemented very well. Mark, you want to make any comments here? Or?
Oh, yes, I had a question. So why did it take 10 years?
It looked easy at first.
You don't have to answer that question.
Well, okay. So, so next I'll tell you something that's been taking 20 years. Once you get to be an old guy, then you can, you have these projects that take forever. So, okay, so this is the last thing I want to talk about. And it uses some a little bit out there mathematical ideas, but really that have practical effect in the Gambit runtime library. So, I want to talk about this. So, beginning around 1998, I started to use non-standard analysis as a heuristic for how to interpret arithmetic in Scheme. So I want to explain a little bit about what non-standard real numbers, how you can think of non-standard real numbers. So you can think of them as sequences of real numbers. Not all sequence, but I'm not going to get into that. Certain sequences of real numbers. And each standard real number is interpreted as a constant sequence. Okay, so I give 2 examples here. I give 2 examples here where you take 0. This is like exact 0, integer 0, fixed num 0. 0 you can interpret it as a sequence of 0, 0, 0, 0. 1 you can interpret it as a sequence of 1, etc. And all these operations here, either plus or times or whatever, they're component wise. So you want to add 0 to 1, you add the first components together, the second components together. You want to multiply 0 and 1, you multiply them, so on. So you see that the rules of arithmetic, they come out the same. I mean, you multiply 0 times 1, you get 0. You add 0 to 1, you get 1. You know, I mean, that's what happens. Okay, so that's for standard real numbers. But now let's do some other examples. Let's do non-standard real numbers. So let's call this number here epsilon. And it's this sequence, a half, 1, a half, a third, and it keeps going. So this number epsilon is greater than 0 because every one of these components here is bigger than 0. Okay, so this number is bigger than 0, but it's less than any positive standard real number. Now, I didn't tell you why, but let's say you say, is this less than a quarter? Well, you look at the first component, and you say no, and the second component, no, third component, no, fourth component, no. But from the fifth component on, the answer is yes, it's less than a quarter. And by the rules we're playing by, which I didn't, explain everything out, if something is true for all but, the first few numbers in the sequence here, if something is true except for these first few numbers, then we say it's true. So that's why I say epsilon here is less than any positive standard real number, because eventually this sequence is going to be less than any positive standard real number. And what's kind of interesting is we can take 1 over epsilon, or epsilon inverse, and this is just take each one of these components and invert it. So you get 1, 2, 3, and then it keeps going. And you can see this is bigger here than any standard real number. So, so this number up top here is an infinitesimal. It's a small, it's bigger than 0, but smaller than everything else. And this thing here is an infinity. It's bigger than everything else. So non-standard real numbers are a little strange, but, they're all right once you get used to them. Okay, so now I want to model floating point numbers. So the question is, how do we think about floating point numbers? So floating point numbers, if you work with them at all, you'll find out that they have things like plus infinity and minus infinity. And we're going to model those with this epsilon inverse and minus epsilon inverse. So these are the epsilon inverse here from the previous page. So epsilon inverse is this thing, this non-standard real that just keeps getting bigger and bigger. So plus infinity is epsilon inverse, minus infinity is minus epsilon inverse. Another thing that floating point numbers have that might be a little strange is they have a plus 0 and a minus 0. And those things I'm actually going to interpret with this infinitesimal epsilon for plus 0 and minus epsilon with minus 0. And, what happens with most numbers, plus 1 is modeled by any sequence converging to 1. Okay, so that's sort of the basic, that's the 2-second version of non-standard numbers. But we could choose other number sequences to model plus 0 or plus infinity. You can imagine other sequences going to 0 or other sequences going to infinity. So now we'll get down to programming. What is, if you multiply plus 0, you're going to get that? If you're going to multiply plus 0 times minus 0, you get minus 0. Okay, that's standard, no matter what sequence you use. But if you multiply plus 0 times plus infinity, it's indeterminate, because this plus 0, the sequence for this plus 0 could be going to 0 faster than this goes to infinity, and so then you could get 0, or, if you multiply epsilon times epsilon inverse, you get 1. I mean, you can get anything. It's indeterminate. It's like indeterminate in calculus, indeterminate limit. So in floating point arithmetic, there's this object called not a number. It's a floating point number that's not really associated with a real number. So this is a one-slide introduction of floating point arithmetic with this non-standard loss. So here's a question for you. Now, previous programming systems didn't ask what happens when you mix exact with inexact numbers. They didn't ask that question. Fortran doesn't ask that question. C doesn't ask that question. They just converted the exact numbers to floating point numbers and carried on. Well, Scheme, let me tell you about Scheme. Scheme tries to do the right thing. Okay? So what we do, we're going to try to do the right thing. And we're going to model exact Scheme numbers here as standard real numbers. So 0, exact 0, this is integer 0, fixed num 0, 3/4, it's rational number. So we're going to model those as standard real numbers, and floating point numbers, all these things, etc., as non-standard reals. So let's go back to the question at the top of the page. What is exact 0 times plus infinity point 0? So we're going to model it as this 0 times epsilon inverse, so it's this sequence of all those zeros times this sequence, 1, 2, 3, and we do it component-wise, so we get the answer all zeros. And this all 0 here means that that's exact 0. So back on the previous page, let's see here. When we multiply inexact 0 times plus infinity, we got a not a number. But over here, if we multiply exact 0 times plus infinity, we get 0. And similar examples are all over the place. And it has lots of implications. This is maybe the most important example in some way. So that's why I chose it. But there are lots of different examples you can do. So if you start thinking like that, and you look through the runtime system, there are lots of effects, there are lots of implications of this kind of thinking throughout the runtime system, especially to simplify the routines for complex numbers. So anyway, so I don't want to give any more details, but I wanted to give some idea of why some of the strange stuff in underscore num.scm is there. So it's thinking like this. So so that's sort of the substance of what I wanted to say, and I think I'm within a half hour. And I just have one last point, and that is to say, thank you, Mark. So I'm going to stop there. Okay. And now I'm going to look at you guys again. Yes.
Well, let me say thank you, Brad, because really, I think that Gambit really benefits quite a bit from its attention to detail in the numerical library, and really that's your doing. So great job.
Okay. Well, thank you.